Hello, we are ByteSight, a master's engineering team from the Johns Hopkins University CBIT program, and we have spent the past year developing a project to fight malaria one image at a time. This project starts with mosquitoes, the world's deadliest animals, which is a title earned due to the deadly diseases they transmit, such as dengue fever, Zika, and the point of interest and most prevalent of these diseases, malaria, which infects 228 million individuals annually, resulting in over 400,000 deaths. 90% of these cases occur in sub-Saharan Africa and affect mostly children under 5 and pregnant women. As a result of this public health crisis, our team of 6 traveled to sub-Saharan Africa, specifically Zambia and Uganda, to learn from those on the front lines of the malaria fight how we might be able to help. Over these 3 weeks, we interviewed over 65 stakeholders at 9 separate surveillance sites across the hierarchy of malaria surveillance employees. This included field and community health workers who are on the ground contributing their efforts every day, to research and Ministry of Health directors who make the decisions, as well as rural families who are most affected by this disease. These interviews helped our group to identify and evaluate needs in the malaria space where an innovation of our design can help make an impact and fill the gap.
So what we found from all of our interviews and ethnographic research was that community-level buy-in is crucial for an intervention in this area. And that can usually be gained by first gaining the trust of church and community leaders as well as healthcare personnel, as they're all well respected and trusted by their larger communities. More specifically, we interviewed workers at many different levels to gauge what the core problems in eliminating malaria were. There are many challenges in this area that span a wide range. Mosquitoes are constantly adapting and developing immunity to insecticides, and resources are limited and must be distributed judiciously to ensure that the highest impact is made with proper supplies. In fact, the importance of having enough information about mosquito populations to inform proper distribution of equipment was emphasized to us by one of our stakeholders in Zambia, Dr. Stevenson. She told us of a time that an ineffective insecticide was being used in an area, not only wasting money and resources, but also leading to the deaths of many people who are left vulnerable to the vector populations that they thought were being controlled. Therefore, we decided to dive deeper into the challenge of providing accurate surveillance information to decision makers as quickly as possible in a way that can be adopted anywhere. The core behind mosquito surveillance is knowing which mosquitoes are in an area. As you see here, there are many different types of mosquitoes, and they all have different behaviors. They bite at different times of day, and some prefer to bite humans, while some mainly bite animals and aren't as much of a concern. As we mentioned before, some species of mosquitoes had developed immunity to certain insecticides that others are still susceptible to. And the most important distinction is that some mosquitoes aren't even able to transmit malaria, meaning that the ability to know when a malaria-carrying mosquito or vector is in an area is made all the more important.
You can see the full pathway on your slide right here. We prevent malaria disease cases by controlling vector populations. That means killing those dangerous mosquitoes we talked about that can carry malaria and not killing the ones that don't. We do this by deploying targeted interventions, and those targeted interventions are informed by vector surveillance. However, we found that vector surveillance data is incredibly difficult to obtain. Field workers trap thousands of mosquitoes every single day, and then entomologists must manually speciate these mosquitoes one by their physical characteristics, sometimes under a microscope, but sometimes that wasn't available. This makes current surveillance incredibly insufficient. Up to 55% of mosquitoes are misidentified. There are delays of 2 to 4 months or more because it takes so long to speciate a single mosquito, and there's a huge labor burden requiring importing expert entomologists. The bottom line is that decision makers are using outdated, unreliable data to allocate control measures, which threatens the effectiveness of vector control programs. This brought us to our need, which is entomologists and field workers need an efficient and accurate way to speciate mosquitoes in order to analyze their population characteristics, thereby informing malaria vector control intervention.
So in addition to validating our need, our ethnographic research also served to help our team come up with the criteria for success for any good solution in this space. Our must-haves is what we learned that needed to be in the solution, and that was to differentiate between Anopheles gambiae and Anopheles fenestis, since they're the primary malaria-carrying vectors in sub-Saharan Africa, and to also be able to distinguish these from non-malaria vectors at an accuracy of at least 90%. Any ideal solution would also be able to have this data centrally available 3 to 7 days after specimen collection. Our nice-to-haves would be able to make these differentiations between species at an accuracy of 99% rather than 90%, and to have any solution easily implemented into the workflow, as the workflow really changes from site to site. Finally, our last nice-to-have is that any good solution would not exceed $300, and this is an estimate that was taken from one of the malaria control sites in Uganda. So our team set forth to investigate the current solutions on the market able to identify mosquitoes, such as wing beat frequency or optical methods of identification. However, these solutions are not ideal because they require live mosquitoes and highly controlled environments and are very costly. And having live mosquitoes in a controlled environment is not very reflective of what actually happens in the field. This led our team to decide on computer vision, which, unlike the other solution, meets the success criteria that we did validate in the field. It's able to identify specimens super accurately at the species level, and importantly, it can use dead or desiccated specimens, which is more realistic and reflective of how specimens are collected in the field. And this led us to our solution ultimately, which is a computer vision system that can rapidly identify disease-causing mosquitoes. Our solution does this by taking an image, classifying that image through our convolutional neural network computer vision algorithm, and producing actionable vector surveillance data that can then empower malaria programs to more judiciously deploy their limited resources in the right places. This is our ByteSight advantage. Compared to other solutions, we're able to have an accuracy of greater than 94%. Our solution is easily scalable. We decrease the training burden because it's intuitive and easy to use. So this allows us to task shift something that before only an entomologist with years of formal training could do, now to local or community workers. And it processes the classifications on the order of seconds rather than several minutes, which is the case with the current manual workflow.
Our solution consists of 4 components: a computer vision algorithm, the optics and lighting, a mechanical embodiment of the optical tool, and a software interface between the algorithm and the user. The core component of our solution is a computer vision algorithm. So what is computer vision? Computer vision is a field in artificial intelligence that deals with how computers can be made to understand digital images and videos. In this process, we give a computer sample images of a particular object, in this context, mosquitoes, with their labels, and allow the computer to extract features and characteristics from those images. With enough images, the computer is able to learn what a mosquito looks like. This is called training. After the training process is done, the computer is given images it has never seen before, and this time without labels. It is tasked with predicting what the images are. The method of evaluating how well a computer has learned is called testing. Our solution uses this approach with images of several species of mosquitoes we have collected in the field and has achieved a remarkable accuracy greater than 94%. Entomologists in the field use a dichotomous key to aid in identification. This key looks at key morphological features of a mosquito. For example, the size of a proboscis in relation to the pulp could give valuable information to an entomologist as to what the species of a mosquito could be. And even though we do not know the exact features that the algorithm looks at, our team ensured that the images we took captured enough details about the mosquito by using different optical configurations and choosing the configuration that gave the best resolution. Our product uses a smartphone's camera coupled with a micro lens to take high-resolution images that are processed by the computer vision algorithm. And the images are taken using a standardized optical taking stand. A mobile app serves as the interface between the algorithm and the user.
We have developed our smartphone application with an intuitive user interface that can be accessible by untrained and unskilled field workers. Once the application is opened, the user will then select to take a photo. This will bring them to this camera screen with enhanced optics and magnification provided by our tool. They will then select to take an image. Once this image is selected, our algorithm will go right to work, identifying and speciating that mosquito. Once this identification is complete, the species and confidence score will be returned to the user. This process can then be repeated over and over to fit within existing workflows. We hope to leverage partnerships that we have developed over the last year of working on this project. We have managed to partner with malaria program funders, entomological research experts, the U.S. Department of Defense, and frontline vector surveillance and control teams throughout sub-Saharan Africa. As we look forward to the next steps in our project, we want to work towards the eventual launch. We have identified 3 key success factors that we must achieve. The first is to achieve accuracy of over 90% with field specimens. The next is to decrease the cost to manufacture of under $50. And finally, we want to enhance adoption through journal publications and pilot studies that demonstrate the effectiveness of our tool. Over the last year of research and development, our team has had many major successes. In business plan competitions, we have placed first and second at the Johns Hopkins Business Plan Competition and Hatch Pitch 2020. We have also had several publications and poster presentations that outline the work that we have done. We also have a manuscript in progress that fully details the work that we have completed on this project. Finally, we have worked to establish product adoption pathways with Navy entomologists, the Walter Reed Bioinstitute, and from President's Malaria Initiative. We want to thank our supporting team of experts from VecTech, the Mata Research Trust, the Walter Reed Bioinstitute, and the Johns Hopkins Center for Bioengineering Innovation Design. Without them, our work would not be possible. We are ByteSight, and we are fighting malaria, one image at a time.